for avoiding out-of-thin-air results.
Can you guys hear me? Well, all right, cool. Thank you. All right. Hi, everyone. My name is Pei Zhao, and I'm from the University of California, Irvine. And today I'll present our work towards understanding the costs of avoiding out-of-thin-air results. And this was done together with my advisor, Brian Dembski. So in the design of programming language, as many researchers have figured out, there exists an outstanding problem, which is the so-called out-of-thin-air problem. And this problem exists in C, C++, and Java. Now let me briefly show you the problem with C++. Now here we have the load buffering example, which has two threads. And in thread 1, we load from X, and then we store the result to Y. And in thread 2, we load from Y, and then we store value 42 to X. Now please assume that everything here is initialized to value 0, and all the loads and stores on X and Y are C++ relaxed atomics. And with the red edges representing the reach-from relationships from stores to loads, the C++ memory model allows the execution of R1 equals to R2 equals to 42 here. And the reason is, and this execution can be produced by processors like ARM because they can actually perform load store reordering in the second thread at runtime. Now, on the bottom, we have a second example, which is the canonical out-of-thin-air example. So here, compared to the first one, the main difference is that in thread 2, we store R2 to X instead of an explicit value 42. So in this example, both stores depend on the previous load. Now the interesting question is, well, for the second example, do we allow the exact same reach-from relationship as the first one and allow R1 equals to R2 equals to 42? To better answer that question, let me show you the graph with the sequence before and reach-from relationship on the right here. Here, this is an execution where the nodes represent memory operations, and the black edges labeled with SB represents the sequence before relationship, which is defined by the C++ memory model to represent program order. And the red edges here represents the reach-from relationship from stores to loads. Now it turns out that these two examples have the exact same sequence before and reach-from relationship. And since the C++ memory model is a so-called axiomatic model, which means, well, it defines some sort of relations on top of memory accesses, and then it defines constraints or rules on top of these relations to specify whether a candidate execution is allowed or not. And now, since the memory model does not define a notion of dependency, it really cannot differentiate between these two examples. Indeed, the C++ memory model formalism would allow R1 equals to R2 equals to 42 for the second example. Or more precisely, it allows R1 equals to R2 equals to any arbitrary value. Now, if we take a closer look at this problematic execution, you can find that there actually exists a causality cycle. For example, in thread 1, the store of 42 to Y is actually caused by the previous load from X, because it assumes that the previous load will return value 42. And with such a cycle, eventually it would appear to us that, well, a store causes itself to happen, which sounds pretty absurd. And indeed, many other researchers have shown that if we allow such executions, it would make both informal and formal reasoning very difficult. And note that if we directly write this program in assembly, no processor would produce this problematic execution. And the reason is that hardware generally respects a notion of syntactic dependencies. However, compiler optimizations generally would be happy to optimize away dependencies. As a result, given compiler optimizations and relaxed hardware implementations, it's just very challenging for us to precisely define and disallow such out-of-thin-air executions in the language memory model. Now, in our paper, we studied two approaches that will enforce slightly stronger memory models to forbid out-of-thin-air results. And we implemented both approaches on top of the LLVM compiler, and we show initial results for both approaches about their runtime overheads. Now, let me show you our first approach, which works by preserving dependencies. This approach is targeted towards a Java-like programming language. So in Java, it is supposed to run untrusted code, which may have data races. Now, to satisfy its security guarantees, the memory model must define semantics for programs with data races. And now that normal memory accesses can have data races, they can potentially have out-of-thin-air results. So our approach must forbid out-of-thin-air results that are produced by normal memory accesses. Now, the core idea is actually from hardware. And the idea is to define a notion of the syntactic dependency at the programming language level in such a way that if a load L may cause a store S to happen, well, we will have a dependency relationship from L to S. And then we require that dependency union reads from to be acyclic so that we can forbid those causality cycles. Now we make sure that our dependency notion is close to hardware dependencies so that we only need to preserve such dependencies in compilers, and then hardware would naturally respect the dependencies at runtime. As a result, the previous problematic execution would be disallowed because there would be a cycle in the dependency and reads from relationship here. Now here I will show a simple example about part of our dependency notion here. Here we have two threads. In thread 1, according to our dependency notion, there would be a data dependency from the first load to the second store, even if we know that the second store would always store value 42 to y. Similarly, in thread 2, we would have a data dependency from the first load to the condition of the conditional branch. And then we would have a control dependency from the condition to the store of 42 to x, even if we know that that store will always execute at runtime. By requiring dependency union reads from to be acyclic, we disallow R1 equals to R2 equals to 42 for this example. Now, please note that our dependency notions capture more subtle cases, such as, well, when the address of a store depends on some load, or cases like when a store is conditionally executed, etc. And we formalized our dependency notion in our paper, and you can find more details there. Now, after we define our dependency notion, let me show you how we implemented this on top of the LLVM. So we found that in the standard LLVM compilation pipeline, both the IR level optimizations and the backend optimizations can potentially break our dependency notion. So let's first see how we preserve dependencies at the IR level. So in LLVM, there were many IR level passes, and we only focus on a select set of 35 passes. And the reason is that our initial experiment shows that the overhead with only these 35 passes enabled is just 1.8% compared to 03. So as a result, in our implementation, we disabled all other IR passes and only focused on auditing these 35 passes. And then we modified those that can break our dependency notion. Note that in these 35 passes, many of them would naturally preserve our dependency notion. And due to time constraints here, I will only mention several passes that we modified to preserve dependencies. We modified the instruction combining pass, which is the pass that would simplify combined instructions into simpler ones, which can potentially optimize away data dependencies. We also modified the simplifying control flow pass, which is one of the major passes that can modify control flow and potentially break control dependencies. Note that we also modified passes that can potentially perform store-to-store reorderings, such as the dead store elimination pass. And the reason is that we need to preserve our address dependency notion. And about that, you can find more details in our paper. And here I will show a couple simple examples to give you a flavor about what optimizations that we disabled to preserve dependencies. The first example here shows that we disabled simplifying instructions that can break data dependencies. And the second example shows that we disabled merging stores that appear on both branches to avoid breaking control dependencies. Now we also need to preserve dependencies at the back end. In our work, we focused on the AArch64 backend, and the reason we did not choose x86 is that x86 generally has a relatively strong hardware memory model that does not allow load to store and store to store reordering. As a result, for x86, the compiler would be free to optimize away dependencies as long as they do not reorder loads and stores in the generated code. And in the AArch64, to preserve data dependencies, we modified the selection DAG-based instruction selection pass. And to preserve control dependencies, we modified the cogent prepare pass and completely disabled the branch folding pass, mostly to avoid merging control flows in the back end. Now let me show you the runtime overheads of this approach. In our evaluation, we used the SPEC CPU2006 C programs as our benchmarks. And we used the stock LLVM 3.8 with O3 option enabled as our baseline. And we ran our benchmarks on a Cortex A72 cores on a Firefly RK3399 board. And there are two compiler configurations that we are particularly interested in. The first one is what we call partial optimization. And this is the modified LLVM with only the selected 35 passes enabled. And the second one is our dependency preserving compiler. Here, I will show the results for the single-threaded benchmarks. Now, the reason why we ran single-threaded benchmarks is the following. Although out-of-thin-air executions only apply in a multi-threaded context, both our approach would incur overheads on both single-threaded and multi-threaded benchmark programs. As a result, indeed, single-threaded programs likely represent the worst case. And the reason is that in a single-threaded scenario, the memory bandwidth is not utilized by any other cores. And the instructions that we added to preserve dependencies are generally not memory operations. So these added instructions, in the end, would have a relatively higher cost. And the graph here shows the results. And the x-axis represents different benchmarks. And the y-axis represents the slowdown over baseline in percentage. So lower is better. And the bars in dark blue represents the results for our dependency preserving compiler. And the bars in light blue represents the partial optimization configuration. And for the dependency preserving compiler, we observed an average overhead of 3.1% and a maximum overhead of 17.6%. And for the partial optimization configuration, on average, we observed 1.8% overhead, which means there is still some room for further optimizations for this approach. Now, we also observed speed up on some benchmarks. The likely explanation here is that some optimizations may counteract the effect of other optimizations. And one supporting observation here is that simply disabling the branch folding pass alone would yield nearly 1.5% speed up in some benchmark. Next, let me show you our second approach, which works by preserving load-store ordering. This approach is targeted towards a C++-like programming language. So in C++, RAID memory operations must be explicitly labeled as atomics. And the reason is that if there's any data race for non-atomic accesses, the memory model would assign undefined semantics for the whole program. Now that out-of-thin-air results will involve RAID operations, the memory model itself already excludes out-of-thin-air results for non-atomic accesses. As a result, for such languages, we only need to consider atomic operations. And in C++, atomic operations are relatively rare, especially the relaxed atomics. Now again, the idea of the approach is to preserve load-store ordering for atomic operations. As a result, we forbid the sequence before union reads from cycles. For example here, if we make sure that the load-store ordering is preserved on both threads, then the red edge here, which is the reads from edge, would not be possible because there would be a cycle then. Now note that this approach is an approximation of the previous dependency preserving approach. And the reason is that whenever a store is after a load, we can conservatively think that the store depends on that load. As a result, it effectively forbids the dependency union rich from cycles. Now, the advantage of this approach is that it does not affect non-atomic accesses. As a result, it does not affect single-threaded programs. Now, let's see how we implement this approach on LLVM. First, for IR-level passes, we've carefully reviewed those passes that can potentially perform load-store reordering. And we found that these IR passes actually does not perform load-store reordering for atomic operations. As a result, we only need to make sure that we add sufficient constraints to enforce the load-store ordering in the back end. Because ARM processors can perform load-store reordering at runtime, like I show here. To preserve load-store ordering in ARM v8, we started 6 different strategies. Now, note that these are alternatives, and it's not that we implemented all of them in the same compilation. So the first option here is to treat relaxed loads as the stronger acquire loads. The second option is similar. We treat relaxed stores as the stronger release. The relaxed stores as the stronger release stores. Note that in ARM v8, there were corresponding fence-like load and store instructions for load acquire and store release. The third option is to insert a fence, which is the DMB-LD fence, before every relaxed store. And this fence would effectively wait for previous load instructions to finish. The fourth option is to add a bogus conditional branch after every relaxed load. And we make sure that the condition of the conditional branch would use the result of that relaxed load so that we form control dependencies from the relaxed load to subsequent stores. Similarly, the fifth option is to add a bogus load, whose address would use the result of the previous relaxed load, so that we form address dependencies here. The last approach or option is to taint the address of an existing subsequent store to form address dependencies, if there's one such store. If not, we just add a bogus conditional branch after the relaxed load. Now let me show you the runtime overheads of these different strategies to to preserve load store reordering. So we used 43 concurrent data structures as our benchmarks, and these are mainly from C++, libcds library, Facebook Folly library, etc. And they cover a wide range of concurrent data structures such as concurrent queues, hash tables, and different synchronization algorithms. And the baseline, again, is the stock LLVM with O3 option. And the processor we used is the same. We ran each benchmark on 2 Cortex A72 core on the same board. Now let me show you the results of multi-threaded runs. In this experiment, we ran each benchmark with 2 threads. And we make sure that each thread was pinned on a single core to avoid too much noise. In this table, we show the results of different strategies to preserve load store ordering. And the results here are normalized to the baseline in percentage. So lower is better. The first column represents different strategies. The second column represents the average overheads across the 43 concurrent data structures. And the third column represents the worst overheads that we observed in each strategy. Now, in this experiment, we found that the strategy of adding bogus conditional branch performs the best. On average, we observed no overhead, and it has the smallest maximum overhead among these different strategies. We also observed speed up on some benchmarks, and this is possibly due to the existence of contention. As a result, in our paper, we also show the results for single-threaded runs. If you're interested, I would recommend you to read our paper. To conclude, here we present 2 approaches that forbid slightly stronger memory models, and we show the initial results on these approaches. And I would be happy to take questions now. Yeah. Thanks.
Questions? Doug.
So first, thanks for writing the most influential paper to me of this year. that has helped people come to a better set of agreements on the nebulous plans for a grand unified memory model across Java and C++. But my main question is, how confident are you that these results hold on other ARM chips?
That's a very good question. And since this is a very practical question, so honestly, I don't know. We better do further evaluations to give you the answer. That would be my best answer, because we really don't know. And sorry. I mean, I don't want to say, hey, it's just very cheap on other ARM processors, and that's not realistic. So I don't know. That's my best answer. Well,
We call that work in progress.
right. Or future work.
Hello. I have two questions. So the first one, you try to define dependency for language, right? Based on some architectural definitions of dependency, right? But those, for example, they might be different for different architectures and even different for, let's say, ARM v7, ARM v8, ARM v8.3, right? So what is your approach of doing these definitions?
So our language dependency notion is very conservative in such a way that it almost accounts for, say, at least ARM v7, ARM v8, or Power, these mainstream processors. It holds. Well, we're not sure, if there's a very relaxed hardware designed by someone. We're not sure. But it's just, if you look at our dependency notion, it's very, very conservative. Basically, it's just as it shown in the program in a syntactic way.
Okay, I think we have time for one more. I thought.
Hey.
Hi.
I missed the first minute of the talk, so maybe you answer that, and I'll just look later. But what's your motivation to prevent this reordering? Because in the end, relaxed as defined currently in the C++ standard means no ordering whatsoever. So this out of thin air result is just respecting the standard, right? Or did I miss something?
It's not, the out of thin executions are not desirable. People want to disallow them because it affects the reasoning, basically, or the general or informal reasoning of the code, which makes it very, very hard. So we really want to disable them, but there's no good way to disable them at this point. So
you want to improve on the standard, basically give stronger guarantees than what's currently given.
That's our approach. Yeah.
Yeah. Okay. Thanks.
Thank you.
Thanks very much.
Thank you.